Hi folks, today we are going to start learning about Isaac Newton and his laws of motion. Weirdly, it's one of these things that has kind of permeated into everyone's or a lot of people's knowledge is Newton's laws, and the one that people tend to remember, the one that people think that they know, is it's actually Newton's third law. They don't realise that they've skipped over number one and number two and gone straight to number three. Um, and they kind of remember it or think of it in a way that isn't really helpful, isn't very scientific, and doesn't really help you do any science. What they tend to remember is for every action there is an equal and opposite reaction, which is all fine and good, but what are the units of action? How do you measure an action? It doesn't really mean anything. Um, So, as triple physicists, I want you to remember Newton's third law as this: for every force, there is an equal and opposite force. Um, that's it. That's the law. But the way that we apply it can sometimes be a little bit counterintuitive, a little bit confusing. So we're going to go through some examples so that we can apply it and use it without ever worrying. There's a couple more rules that I'm going to add so that we can use it really, really well every single time. Uh, so when we talk about Newton's third law, for every force there's an equal and opposite force. This is why whenever you push a door, you can feel the door kind of squishing into your hand, or when you're standing on the surface of the earth, standing on any surface, you can feel it in your feet. Um, it's a way of thinking about it's a way of thinking about the world. When we combine it with the other of Newton's laws, we can start to analyze problems. So, two extra things that I want you to add to your understanding of Newton's third law. One is that these forces always act on different objects. We are going to do lots and lots of force diagrams, and we're going to look at lots of forces acting on one object. So something getting pushed and pulled and lifted and dropped and all sorts of things. That's a different part of Newton's laws. At the moment, we are just considering Newton's third law. They always act on different objects. So there's an example: you push the table pushes you. Okay, you've always got to have two objects and they're acting on each other. So there's you pushing the table, and then nothing else pushes the table, but the table pushes back on you. The other rule is that they're always the same type of force. So if the planet exerts a gravitational force on its moon, so the moon has got a weight, then the moon is also exerting a gravitational force on its planet. It doesn't it doesn't do friction or drag or air resistance on the planet. It does the same thing. Same with the previous example: you push the table doesn't decide to do air resistance or friction or anything like that. It pushes back. If you pull something, it pulls back. Um, yeah, I've run out of examples. So focusing on gravitational fields, then focusing on the weight of something. Um, Gravitational field strength of the planet Earth is what causes you to have your weight. You've got mass, regardless of whatever planet you're on, whether you're in space, anything like that. You've always got your mass, and it doesn't change. Back in year 7, you probably did some kind of activity where you measured your mass, or you measured the mass of something, and then figured out how much it would weigh in newtons on different planets. And you found that the bigger the planet, the more massive the planet, the more you would weigh. That's why, or one of the reasons why, if you went to Jupiter, you would be crushed. Why, if you go to the moon or Mars, you can jump really high. Your mass is the same, but your weight is less. so you find it easier to jump around. Weight is a force, it's just a type of force. And we looked at vectors last time. Force is a vector because it's always acting a certain direction, and your weight is always acting towards the centre of the Earth. It's not technically acting towards the surface of the Earth, although that's what it feels like. If it was only acting to the surface, then if you dug a hole, you could float around inside the hole or be attracted to the surface upside down. So even if you dig a really big hole, you're still attracted to the bottom of the hole because you're actually being attracted to the very centre of the Earth. So that vector, the direction of that force that the Earth has put on you is towards the centre of the Earth. But you've got a mass, so you've also got your own gravitational field. And there's nothing special about the planet Earth, nothing special about the Moon or the Sun or Jupiter or anything like that that means they get a gravitational field. It's just that because they are so massive, their gravitational field is very strong. That's why we can feel it. But we've got gravitational fields ourselves. Cars and buildings and mugs and dogs, everything's got a gravitational field, but because they're so tiny compared to the Earth, we don't really notice it. So when we're looking at this, the gravitational field strength of the Earth pulling you towards it, so you've got a weight on the Earth, your gravitational field strength is also pulling the Earth towards you. The Earth has a weight on planet U. Because your gravitational field strength is so vanishingly small, the weight of the Earth on you is exactly the same as the weight of you on the Earth, which is why this massive thing doesn't squash you, because you're only pulling it towards you a really tiny bit compared to other objects. So the equal and opposite part, it doesn't matter how much of a force you apply to an object, it will always apply the same force back. These forces are always balanced, so they're the same magnitude, the same size, and acting in opposite directions. So for example, if you push a wall just a little bit, it will push back just a little bit. If you push it harder, it'll push back harder. Here I'm representing a larger force by increasing the length of that arrow. If you push the wall really hard, it's just going to push back really hard. Nothing's going anywhere. So you push on the wall pushes on you. Obviously, you can do things to eventually push over the wall or destroy the wall. That doesn't mean that you've somehow pushed harder than the wall, that there has been an imbalance there. The situation just gets a lot more complex. We don't deal with this kind of situation, but I just wanted to make sure that you know that even though you can eventually knock down a wall, throughout that, the Newton's third law is still satisfied, it's still balanced, it's still equal and opposite. There's just, as I say, it's a bit more complex, and what you've essentially got is the force of the big hammer being spread across lots of little pieces of wall. So even there, the forces are still equal and opposite. First activity then. There are at least 5 pairs of Newton's third law forces in the picture below. I want you to have a go, see how many you can identify. Remember, they're always the same type of force and they act on different objects. So pause the video now and have a go. Okay, we'll now go through some answers. You could have the friction of the ball on the bat and the friction of the bat on the ball, where they collide with each other. You could also have the friction of the person's hands on the bat and the friction of the bat on the person's hands. This is all taking place on planet Earth, and all of these things have a mass, the ball, the bat, and the person, So we could have the weight of the ball on the earth and the weight of the earth on the ball, even though it's not touching the earth, even though it's not on the surface of the earth. Things don't magically lose their weight when they go into the air. The weight of the bat on the earth, and the weight of the earth on the bat, and the weight of the person on the earth, and the weight of the earth on the person. Another example, which is a bit more fun, a bit more weird. In 1610, Francois Ravaillac commits regicide by killing King Henry IV of France, and he was sentenced to execution by dismemberment, where a horse pulled on each of his 4 limbs, like this. Can you identify all 13 Newton's third law pairs involving Francois and his execution? For the purposes of this, I'm only interested in Francois, poor old Francois in the middle here, the ropes, and the horses. I'm not interested in the guy here who's about to quarter him. I'm not interested in the weights, the masses of any of these people. Not interested in these poor blokes getting burned. Not interested in this guy with the whip. I'm only interested in this guy and these 4 horses. Give you a bit of a hint. The friction of the rope on Francois's left hand and the friction of Francois's left hand on the rope. Pause the video now, have a go. Here are some answers. So, the first one I gave you in the example, friction of the rope on his left hand, friction of his left hand on the rope. We could also have friction of right hand on rope and friction of rope on right hand. We could have friction of the rope on this horse and the friction of the horse on the rope, and the same again for the feet and for each of the 4 horses. We could also have the weight of this horse on planet Earth and the weight of the horse, the weight of the planet Earth on the horse, and this horse, and this horse, and this horse. And we could also have the weight of poor old Francois on the Earth and the weight of the Earth on poor old Francois. You have another activity to do and an extension. Enjoy.